Okay, if not the map of the properties of the ideal gas mixture, which I denote as IgM, key properties are that the partial molar volume, any component in an ideal gas mixture is the same, is equal to RT by P, which is the pure component specific volume of the ideal gas, the specific volume of pure component ideal gas, which means the volume of the ideal gas is simply nRT by P, where n is equal to so we can write the equation. This gives the equation of state of the ideal gas as PV equal to nRT in terms of the total volume. And further, this is the ideal gas mixture only. The partial molar internal energy of every component is equal to the corresponding specific internal energy of the ideal gas, which, as we know, is a function of temperature only. Similarly, for the enthalpy, now the ideal gas mixture is the partial molar entropy of each component is given by the specific entropy of the ideal gas at the same temperature and pressure as the ideal gas mixture, plus or minus a quantity or logarithm of yi, where yi is the mole fraction of the component I in the ideal gas mixture. So what we see here is that in general, of course, all for an arbitrary mixture, each partial molar property will be a function of the temperature, pressure, and the mole fraction vector. All mole fractions might come into play. So even for the ith component, if you take partial molar property, it will be dependent on the composition of the mixture as a whole, not just the composition of that particular component. That is very general. However, in this case, we see that in fact the partial molar volume of the ideal gas mixture is dependent only on the temperature and pressure. It is independent of the composition. Similarly, the partial molar internal energy and enthalpy are a function only of temperature, not even pressure comes in, not the composition. If you look at this though, this partial molar property of the entropy of any component in the ideal gas mixture is a function of both temperature and pressure and the composition, but it involves only the fraction of the particular component that I am interested in. Similarly, of course, A also you can write, but I don't recollect it. But G is coming from can be given as GI. Plus RT again, this is a chemical potential of the ith component, dependent only on the mole fraction of that particular component. So that shows how special the ideal gas mixture is. So now taking any property, let's say such as the enthalpy, we want to calculate the mixture, that is, let's say H mix at T2 and some composition Y, that I am not going to change for simplicity, minus T1P, so two states of the mixture. Now we are back to the level of mixture, any mixture, not necessarily ideal gas mixture. We said that I can write this as delta of H. We have already seen how to do this. This is almost identical to the calculations for the pure component, except that you have to calculate the mixture parameters of the equation of state for the particular mixture using some mixing rule, any mixing rule that is available to use. right? So that will depend on mixing rule also, how the formula, the calculation. We will do that with a simple problem. But now we'll take up how to calculate the change in any property of the corresponding change for the ideal gas mixture between the same state. Now just do it for H and S, and you can easily get the other results for the ideal gas mixture. So here if I were to do it, now I am considering only the ideal. This is what this means, T2Y. This is what this delta means actually. So how do we do that? The answers are clear from the formula here. So I will simply write this as sum over. This is nothing but yi hi dm I equal to 1 to c. Evaluated, I will here put e2 y. Although we know that the partial molar property of the enthalpy for the ideal gas is dependent only on temperature. And then this has to be the general formula for any mixture. But now I am going to apply it for the ideal gas mixture. So clearly this can be written as sum over I equal to 1 to c. yi will be common factor. This depends only on the temperature, so this would be H. That's all, quite straightforward. Now what can I express this in terms of the change of the ideal gas between two temperatures? What can it be written as? In terms of the specific heat, right, of the ideal gas. The whole idea is I have the equation of state for the actual substance and the heat capacities of the ideal gases. Now we see that the same would apply for the mixture, because the mixture is, we can see here is dependent on the properties of the mixture, properties of ideal gas mixture, dependent on the some kind of an average over the ideal gas, pure component ideal gas properties. So this can be easily now written as sum over I equal to C y I C P I which will be E1 to E2. So this is what this is, and I can also sort of show that the sum and the integral can be interchanged, and I can write this as integral E1 to E2 sum over the function of temperature. This is one way of writing it, another way of writing it. Now if I assume that the specific heats are all constant, or I can use some kind of an average specific heat over the temperature range, if I can assume the ideal gas specific heats to be constant approximately, then obviously I get a simpler formula. So if I, let's say, use an average value, then what would I get? So then this would be a constant. So I will simply get sum over I equal to 1 to C y I C P I times E2 minus E2. So while for the individual ideal gas, so in some sense the ideal gas mixture here, the enthalpy change is a weighted average of the, you can say it's a weighted sum of the individual ideal gas properties. Because the ideal gas alone individually, then we would have all the sum. It would simply be CPI IG times T2 minus T1. So we can ask what happens when it's a mixture of ideal, it's an ideal gas mixture, then it would involve the specific heats of the, this can be regarded as in some sense as the Cp IgM itself. I can write it like that. I can define the specific heat of the ideal gas mixture in that way. We don't have to do the formula is there as it is, but because the values of the individual specific heats, I can simply calculate this interval. Or if it's a function of temperature, where you have the A0 plus B1T plus A1T and so on, that also you can easily calculate. And the formulas are written out in, for example, YBC also has a long list of these formulas in terms of the A0, A1 and so on. We won't go into it. Let's now take the enthalpy. So I can again write this as how I do want to see yi si em igm evaluated at T2 minus so this would be now the enthalpy, the entropy partial about is dependent on both the temperature and pressure as well as the mole fraction. Right? But you will see that because the change between two states having the same composition, the part corresponding to the mole fraction will simply cancel, which it will not if the compositions are different. So I can anyway write out the formula first times this would be SIIG, this is the function of temperature and pressure, minus R log yi E2B minus so clearly this sum y over yi log yi will cancel with this, right? So I can get rid of this, and so I have again sum over I equal 1 to C yi times so what is this? How do I calculate this now? We've already done this for the pure component ideal gas, so that's all we need to know. So, but how would you do it? What is it equal to? What is it? Can you write it? Remember? You come and write. How would you calculate? Now this is a function of both temperature and pressure, and the integral. Actually, this is. We have to write it as an integral. How would you just take this? I don't want you to confuse with the. Now I will do it for each ideal gas. So the properties of each ideal gas will come. First, write it as an integral. That is the first thing you have to know how to do. The integrals again will separate here, otherwise it will be a bit tricky to do the integration. So this ideal gas, right, will separate out. How did you get this? If you remember the formula written, first of all, the formula has an error. This is the problem, when you just memorize the formula and write it, you're bound to fall into error. Right? How did you get this in the first place? Yeah, when you come to the board and write the preceding step. What is important for me is the method, not the answer. Answer anyway is there in the book. So you can ask me, do we need to know the method, right? No, it's not a double integral. It's not a, you can, okay, fine, let's see what we write. No, don't be so careless. Just watch what you're writing. Yeah, fine, that is fine. But no, your dt, when you have a derivative with respect to t, so this is not, yeah, this is, then, what is ds ig by dt? Cp I ig, yeah. This is CPI. First of all, it's not proper to write it like this. It should just be T1, okay, you can go back. T1, T1, 2. So otherwise it looks like a double, it's not quite a double integral. It's actually a path integral between the two states, T1, T1 and T2. It is not quite like, if you want to write it like you did, that would be it. You have to be careful about you cannot invent some new mathematics, right? That's not our job. We just follow what the mathematicians have invented and we are just applying it, and you should apply it faithfully and correctly and not, come up with your own notation, right? So this is a different, this might not be correct yet, if you choose a proper path. So this is where it is, and it so happens that this is a function only of temperature. The integral, which is actually a path integral, the two-dimensional temperature pressure domain, splits into two separate integrals of the form a to b f of x dx. So you have to understand that. So happens because otherwise you have to construct a path and do this for any given substance. Because the ideal gas is again SI, that is very important. So now these errors also point to some common errors. Now we are dealing with C different ideal gases. So it's very important for you to distinguish one from the other, because the heat capacity of one ideal gas will not be the same as that of the other ideal gas. Right? You have to understand that. And further, so this is this. What is this? This turns out to be is independent of the ideal gas. So this is actually minus R over P, ds by dV, as we have seen from one of the Maxwell's relations, is actually minus dV by dt, which for the ideal gas becomes minus R. You have to understand all this and not just, the test is not to see how well you remember these formulas, but how well you can construct the steps that lead to these results. So this is fine. So if I were again to treat so now this can be written as I equal to 1 to c y I integral, right? T1 to T2, having seen that it separates out dt minus the other integral, of course, can be immediately integrated R log T2 by T1. So this again I can take the sum into the integral, and for a constant specific heat I can write it as sum of the y equal to 1 to c y I Cp I Ig bar some average minus R log P2 by P1. Because the other one should simply be I equal to 1 to c y I multiplying minus R log P2 by P1. So that adds up to 1. The sum of all the mole fractions is 1. Right? So this is what we get for the entropy. You can easily calculate what it will be for the internal energy. You can easily guess that it's going to be replaced by CPI, right, times T2 minus T1 for a constant specific heat. Otherwise, you have to integrate CPI. You have to understand all this. Cp is what is given normally in the table. So if you want Cp, this for the ideal gas, subtract minus R from Cp, then you will get Cp. So you have to be aware of all this. So let's now take a problem, and numerical problem, and see how to applied these ideas. I have to spend too much time on it because this is very much like the pure component. When we see the ideal gas mixture, you know how to calculate the pure component ideal gas properties, you can pretty much do it. Right? So there's not much difference. Only point is that you have to now take into account the fact that you have many components in the mixture, both in the equation of state in the actual substance and while considering the ideal gas mixture. So we now have ethylene-propylene mixture, which I call it 1 and this is 2, and the mole fraction gas mixture. This is a binary mixture and it undergoes from a state to another state which is represented by, so both change in temperature as well. So you have to understand that here T1 correspond to the state, first state and not to, whereas here when I write Y1 the subscript corresponds to the component, so you should not get confused between the two. I can't find any better notation. Maybe we can come up with a better notation. Since we have already used this, probably a better way to do it would be to do this. Right? But I'm not going to do it. And so we leave it as it is. Now we are going to use the van der Waals equation of state. And for ethylene, which is component 1, the van der Waals equation of state for parameters are given like this. So I'm going to use the standard, first we'll calculate the equation of state parameters. So the equation of state is T equal to RT. Everything corresponds to a mixture. When I write it like this, obviously the V, P, T all correspond to the volume, pressure and temperature of the mixture. So I'm only distinguishing the parameters here. So B mix is now this is the, unless I mention, you can simply assume this in an exam, unless I specify something different. These are general formulas. Now you can apply it to the specific case for binary mixture. So can you calculate the B mixture and A mixture? Ravi, Teja, Gurapati, can you come to the board and how would you calculate B mixture for this particular case? You can supply the numerical answers. I want just to apply these formulas, very straightforward, nothing but substitution. So I've given the values B1, B2, Y1, Y2. So Z now we are using Y because the gas mixture and using the standard convention. Yes. Yeah, okay. Fine. There's no need for a sum here. So anyway, add it 0.3 times P2. Very good. 8 point. Maybe it will be somewhere in between the two. Okay, fine. So give me, you can calculate the answer and give it. Calculate A mix. This is a slightly more complicated. 4 terms will be there because I equal to 1 to 2, J equal to 1 to 2. The coefficients are A11, A22, A12 and A21. Now you can easily verify from the formula Aij equal to square root of Aij. A11 will be equal to A1, A22 will be equal to A2 and A1 for a binary mixture there will be 4 terms. For C component mixture there will be C times C terms. Right? So you have to be very careful. But for a binary mixture, A12 and A21 would both be equal, and they would be equal to square root of A1 times A2. So all the calculation will make the calculation of A slightly more complicated. Let's see, good. Yeah. Z1, what we know, yeah, but there's no Z. Zi, you have to first understand this formula. There's only one subscript for the mole fraction. There are no 2 subscripts. Yes. Fine. Another term from A21, which is of course equal to A1. Yeah, fine. Very good. So now A11 is going to be A11. Yeah, square root of A1 times A1, which is A1 only. Right? So you can easily guess this. Now the Aij applies to C component mixture. You are taking 2 components at a time and calculating. Here of course we have only binary mixture, so you should not confuse the 2. Z2 square and completing it. Yes, so now at least A would substitute the numbers 0.453. What is Z1 square? 0.49. 0.7 square, 0.49. Yes. Plus, so you can give the answer, somebody can calculate and give the answer. 0.3 square plus 2 times square root of 0.453 times 0.845 times 0.7 times 0.3, which is 0.21. Yes. Times 2. Yes, that's fine. So can someone give the answer? B mix is? A mix. No, first give B mix. 6.5 roughly 10 to the minus 5. If you more units again are very important, consistent units you have to use. And the A is 0.5579. Okay, A is point, I can make it 0.55 E. Newton meter power 4 per mole square. Now, the first step, so now we take up the equation of state calculation. Let's take the enthalpy change, right? So we have already seen that H minus, if I look at the formula for the pure component, H minus P1, right, is, you'll see that is RP1 times, or maybe I write it in terms of P1 minus RP1 plus integral infinity to V1 P1 dV by dt dV. Now for if we execute this for a van der Waals equation, I can directly go to the van der Waals equation state for the pure component. From there infer the mixture, right? So the value for the van der Waals is P1 minus RP1. If I calculate this integral for the van der Waals equation state, it's going to be minus A over V1. So now the clue that I gave for now inferring the property, because we are going to stick to van der Waals for the when Robinson, there will be a slight complication in terms of the fact that one of the parameters is dependent on temperature. Actually, there are 3 parameters, so we see how to handle it. That will become an issue that we are calculating, for instance, dV by dt. You have to take that into account. You see how the mixture rule applies there, and I'll point that out. But now, what I'm going to infer is that you can easily verify this. So why? particular mole fraction. So I'm not going to put a superscript or subscript on that one, any mole fraction. That would be P1, same formula, P1. Now, just to ensure that you understand this is now going to be the volume of the mixture, minus R P1 minus A mix, which is of course the function of y by P1 of the mixture. This is what you have calculated actually, A mix, because the composition is remaining the same. So both the states this A mix would work. So clearly now what is the first thing I have to do to calculate H minus HIGM? P1, right? So I already have that calculated, that's why I am doing this, because I have calculated it using some means, and so you can take this as given approximately. What I am having is that P1 mix, so the way I calculate it is go to the equation of state, substitute these values of A mix and B mix, and calculate P I know P1 is 323, P1 is 10. So all the two you probably get only one real root, that is my guess. So we take that the height real root is 2.537 into 10 power minus 3. So clearly indicating of a gas state. You just look at the V. A better way to look at it is also calculate Z1 mix. It is P1 mix by RP1. Because we have seen that for the ideal gas mixture also PV by RT is 1. So the calculation of PV by RT for the mixture will give an indication of how close we are to the ideal gas mixture state. And you will see that this is roughly 0.945. So we have that, and now the calculation for, so here obviously what I would put is P1 are given 323 and 10 bar, P2 Y. The B2 mix will change, not because the composition is changing, but the pressure and temperature are changing. Now B2 mix, I have also calculated. These are the most difficult parts of the calculation. So I am giving you the answer is 7.9 times 10 power minus 4 meter cube per mole. That's what I have. You can easily verify this. And the Z2 also continues to be close to 1, which is 0.95. The pressure is increased, temperature is also increased, so it is still can be considered. Anyway, it is not of our concern. This is what we are getting, right? So now, how do you calculate this? So all I have to do is to subtract these two. So the delta, right? So the delta, if I don't want to erase, this can be erased. This is B. These I want to keep it. So probably we don't need this also. We have already used it to calculate the V. But anyway, I'll leave it as it is. So now delta H max minus HIGM is equal to B2 mix minus B1. So I'm going to put the mix. Now you know that I'm referring only to the mixture. Minus B1 minus R times B2 minus B1, and then minus A mix times 1 over B2 minus 1 over B1. We need the A mix now because I need to substitute. So I have to calculate this. So let's write it in the proper units. So P2 times B2 would be 60 bars. So it would be 60 into 10 power 5. B2 I have 7.9 into 10 power minus 4 minus P1 is 10 into 10 power 5. So units are very important. B1 is 2.537 10 to the minus 3. Then minus R, we use joule per mole, and T2 minus the whole answer is going to be now in joule. H is a specific property. It's going to be joule per mole. That is very important. You have to be consistent with the units. T2 minus T1 is 600 minus 323. And then minus A makes us 0.55A times 1 over V2, 1 over 7.9, 10 to the minus 4, minus 1 over. So, what is the answer that you are getting? You can calculate this. Okay, the answer I am getting is roughly minus 0.586. The answer will be joule per mole, but I am going to write it kilojoule per mole. Right? The final answer is minus 0.586 kilojoule per mole. So now what we will do is look at the other contributions. And you will see that the contribution coming from this can almost be neglected. So it's also important. This is only an example to help you understand the calculation. It is also a good pointer to how to decide whether the ideal gas mixture will be sufficient or not. Right? So in this case, what about delta HIGM? So I'm going to assume a constant specific heat for simplicity, but you can do it is varying, it's not a constant. I'm using some average. The CP1 IG at 323, I roughly calculated to be 46.37 joule per mole per Kelvin, and at 600 it is 71.64. So obviously this has a fairly important temperature difference. You cannot just assume it as a constant, but actually use an average. I just took the average of the two and calculate a rough average T1 to be 59 joule per mole per Kelvin. And similarly, for you can do a more rigorous calculation because I've given you the identity of the Q's pH, green and probably you can go to the tables and get these values. So this is 87.75, even so now the delta HIGM, as we have seen for constant specific heat, is sum over I equal to 1 to 2 here. YICPIIG times T2 minus T1. So this would now be 0.7 times 59 plus 0.3 times 87.75. That is sort of like an average specific heat for the ideal gas mixture. It is simply the weighted sum of the individual specific heats. And the answer, so this is 600 minus 323, the answer turns out to be 18.732 kilojoule per mole. If you compare, this is almost negligible, 0.5. By 0.5 by roughly 20 minus 0.5. And so if you look at the magnitude, it is decreasing a bit. Minus 0.58, roughly the order of 1, that is around 20. So clearly the error is of the order of 5% error you would incur if you neglect this. So clearly this is probably, what this shows is that I could have simply done the calculations for ideal gas mixture, which is very simple directly, rather than spending all this time. But anyway, it illustrates what you have to do in case you have to take into account the effect of the non-ideality of the gas mixture. Here it is very small. So the same way, what I will ask you to do also is to do the calculation for the entropy, same values here, A mix, B mix, everything is already there. So now what I got here was that for the entropy, I'll just write the answer using the same approximate values. I got delta of S mix minus SIT. So I will use it as an exercise for you to do. So the minus 0.45. Here it seems to only joule per mole. I have to verify that. But anyway, you can. I think it's only joule per mole. And then delta S ITM. You have to add the two. I'm just giving the individual contributions is 26.98. Again, you can see there's hardly any contribution from the non-ideality. Very negligible compared to that. So these are fairly good. The 60 bar is a high pressure, but temperatures have increased. So ideal gas mixture seems to be a very good approximation in this case. But we have also seen how to calculate the properties of the mixture equation of state, right? And also the procedure is the same, how to infer the formula for the mixture calculation from the corresponding formula for the pure compound. So what I will do is go to the formula for S minus SIT, get what this is for the Van der Waals. We've already got the expression, right? And then calculate this. Because V1, V2 is given, so you can easily do only substituting is required. You do that. Now for the other part, the ideal gas will obviously be log T2 by T1 and all of that. But Cp, you can use the same average specific heats and simplify the calculation. Are there any questions? Now when you come to other equation state, let's say as the pen constant, just here the confusion about the notation. Because what we have called, for example, we take the pen constant, it is P of the SRK minus A alpha SRK, because I remember the B quite well. So now how does the B, it's the same, B there is no temperature dependence, so the mixture rule can be applied like that, there itself. But now, what many books of course call this as A of T. My only problem with that is that, while A is regarded as a function of temperature here, you are also giving A the same symbol to a constant. So which is why I have not given any symbol for the two together. I am just writing it like this. A is a constant you find from the conditions at the critical point. Strictly, if you call the product A times alpha of T as A of T, then what they call as A should strictly be A evaluated at TC. And it's clearly not proper to give it the symbol A, right? Because it's a function of temperature on the one hand, and on the other hand, on the right hand side, you're claiming it's a constant. So we leave it as it is, but how? If you look at the way the mixing rule is applied, it is applied to the product. Because it is very easy for them to write it because they are calling it as A, the product together. It is only now a function of temperature. So the same thing would apply. So this would be AI of T. Everything would be a function of temperature. So what we would do is simply look at apply the mixing rule to the product A times alpha. So the alpha will also depend on the individual component. Right? So I can write now A alpha. Either it can be SRK or PR or whatever else you want to have. Of the mixture would be sum over I equal to 1 to C. Z A would be there, and I would we call this A alpha ij, right? Where A alpha ij would be square root of, so this is not the only, for some books also introduce another factor to the Aij formula. They introduce something called the Kij, which could sometimes be a function of temperature house further. Right? So now A alpha ij, I'm going to call this as A alpha I times A alpha j. So now I can split it, right? And this will be square root of Aij, right, times alpha I alpha j. So both have to be taken into account. So if you are just calculating the value of A mixture, suppose let's say you want to again do the same calculation, where given P1, T1. Now I want to find P1, let's say. I'm using the SRK equation of state. So how would you do B mix same formula, but I have to use the B because there is another inconsistency in the notation. Because there is van der Waals or SRK up here, I am calling everything as B. So it should be B van der Waals, B, PR, B, SRK. Right? So that anyway we are used to it. So I have to go to the Ben-Robinson parameters, B parameter or SRK parameters. So when there is a different set of parameters in terms of P, C, P, C and so on, calculate the individual ethylene and propylene, Ben-Robinson of SRK. Then I need to calculate the A mix. For us actually it is A alpha mix here. So obviously the same formula would apply. So this now, the parameter calculation itself will depend on temperature. So this is actually depending on not only on Z, but it's also depending on the temperature. So what does that mean? That means that for T1 I will get a different A alpha for the mixture. For T2 I will get a different one because alpha is dependent on temperature. Now when you go to the entropy calculation, you will see that there is a term dP by dt which we saw would require calculating the dA by d or d by dt of A alpha. Effectively for us, it will be calculating d alpha by dt. So again, you would have to apply that to this formula. So the square root of alpha I alpha j that has to be differentiated with respect to temperature. We see what I would suggest is you take the same problem and try to apply it to SRK and at least see what complications you are getting. At least try to calculate B mix and A mix, even if you don't proceed to calculate the volumes, and see what further complications would arise when you are calculating the entropy of the formula, or the entropy change, right? Where the dP by dt comes in the integral and how this could modify for the mixture. So I want you to think about it before you come to tomorrow's